In previous lecture, we solved question up to question number 4 from exercise 1.2. Now today we solve question number 5. Using derivative, prove that sub question 1 tan inverse of x plus cot inverse of x equals to pi by 2. Number second, sec inverse of x plus cosec inverse of x is equals to pi by 2. If you study trigonometric function chapter from part 1, there is one more property, that is sin inverse x plus cos inverse x equals to pi by 2. So we prove that with the help of trigonometric functions, inverse trigonometric function. So here we have to prove this property by using derivative. So see first question. Now see the solution of first sub question. So we consider this LHS as function f of x. So we write here, let f of x is equal to tan inverse x plus cot inverse x. So we denote this function as equation number 1. We differentiate this function with respect to x. So differentiate with respect to x. We get derivative of f of x as f dash of x. Derivative of tan inverse x is 1 upon 1 plus x square, plus derivative of cot inverse x is minus 1 upon 1 plus x square. So when we remove the brackets, we write 1 upon 1 plus x square. Here plus minus minus 1 upon 1 plus x square. So its difference is 0 because both the terms are same. So f dash of x equals to 0. And we know that when function is constant, then its derivative is 0. So we write here, therefore f dash of x equals to 0. So here this function f of x is constant, so we consider that function f of x equals to k. So we denote this as equation number 2. Now we have to show this f of x is equals to pi by 2. So for that, from this equation number 1, so we write here, for any value of x, f of x is equals to k. That means if you take any value of x, we get value of that function equals to k. For example, if we consider here, f of x is equals to 2. When we replace x by 0, we get 2. When we replace x by 1, we get value 2. That means we get the value 2 always, because function is constant function. So we consider here value, let x is equals to 0. So that value we consider x equals to 0. Therefore we write f of 0 is equals to k. Now from equation 1, when we replace x by 0, so we write here, from equation 1, f of 0 is equals to, so we replace this x by 0, so we write here tan inverse 0 plus, we replace here x by 0, so we write here cot inverse of 0. Tan inverse of 0 is 0, cot inverse of 0 is pi by 2. So we get here f of 0 is equals to pi by 2. So we denote this f of 0 equals to k as equation number 2 or equation number 3, and this as equation number 4. So from equation 3 and 4, we say k is equals to pi by 2, and we consider f of x equals to k. That means f of x is equals to pi by 2. Now from equation 1, f of x is tan inverse x plus cot inverse x, and here we get f of x is equals to pi by 2. So we denote this as equation number 5. So we say here, from equation 1 and 5, tan inverse x plus cot inverse x is equals to pi by 2. Now next we solve sub question 2. So see second sub question. So we consider this function as f of x. So write let f of x is equals to sec inverse of x plus cosec inverse of x, and here condition is mod x greater or equals to 1. That means we have to consider here value of x which is greater than 1 or equals to 1. So we discuss that at that step which value we have to select here. So first we differentiate this function, differentiate with respect to x. Now derivative of f of x is f dash of x, derivative of sec inverse x is 1 upon x into under root x square minus 1 plus derivative of cosec inverse x is minus 1 upon x into under root x square minus 1. So we remove the bracket, 1 upon x into under root x square minus 1 plus minus 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 1 upon x into under root x square minus 1. So here its difference is 0. So f dash of x equals to 0. That means f of x is constant function. Therefore f dash of x equals to 0 implies f of x is constant function. So that constant we consider here k. Therefore let f of x is equals to k. So for any value of x, so here condition is mod x greater or equals to 1. So we consider here let x is equals to 2. Mod x greater than 1 we consider here. So let x equals to 2. So from this equation 1, so we denote this as equation 1. Value of f of x as equation number 1. Therefore from equation 1 f of 2 is equals to, we find f of 2 from this. So we get here sec inverse of 2 plus cosec inverse of 2, and we know that sec pi by 3 is 2. So we write here sec inverse of 2 as sec inverse of 2 as pi by 3 and cosec inverse of 2 as pi by 6. So if we make base same, for that we have to multiply and divide by 2 here. So we write 2 into 3 plus pi by 6. So we get here 2 pi plus pi, that is 3 pi. 2 into 3 6. So base is same. So we write this as pi by 2. Therefore f of 2 is equals to pi by 2. Now we consider f of x equals to k. Therefore f of 2 also k. From this we say k equals to pi by 2. Therefore k equals to pi by 2. Now we consider here f of x equals to k. That means f of x is equals to pi by 2. But from equation number 1, f of x is sec inverse x plus cosec inverse x. So we write here from equation 1 f of x is equals to sec inverse x plus cosec inverse x, and this is value equals to pi by 2. So in this way we get sec inverse x plus cosec inverse x is equals to pi by 2. Now see main question second, sub question 1. Question is differentiate the following functions with respect to x. So here first sub question is tan inverse of log x. That means we have to find a derivative of this tan inverse of log x. So we denote given function as y in solution. So write let y is equal to tan inverse of log x. Now this tan inverse is composite function because we know the standard form. D by dx of tan inverse of x is equal to 1 upon 1 plus x square. Here instead of x value is log x. That means also we have to find a derivative of log x. So for that we know the derivative of log x. Derivative of log x with respect to x is 1 by x. So we use these two standard form for differentiating this function. So write differentiate with respect to x. Now derivative of y with respect to x is dy by dx. Derivative of this outer function, so derivative of tan inverse is 1 upon 1 plus x square. So in place of x we have log x, so we write 1 upon 1 plus log x its bracket square into derivative of log x. So we write this as 1 plus log x its bracket square into derivative of log x is 1 by x. So write this 1 by x at first position, or you can write this as 1 upon x into 1 plus log x its bracket square. So this is a derivative of this given tan inverse log x. Now see second sub question, cosec inverse of e raised to the power minus x. So first we see here how many derivative we have to find in this function. So here cosec inverse is outermost function. So first we have to find the derivative of this cosec inverse. Then we have to find derivative of e raised to the power minus x. Then we have to find the derivative of minus x. That means we have to find total 3 derivative. So we denote this function as y. So write in solution, let y is equals to cosec inverse of e raised to the power minus x. First we confirm how many derivative we have to find. So we have to find 3 derivative. So we write here, differentiate with respect to x. Derivative of y is dy by dx. Derivative of cosec inverse x. So first we write here formulas, d by dx of cosec inverse x is equals to minus 1 upon x into under root x square minus 1. Then next we have to find derivative of e raised to the power x. Derivative of e raised to the power x is e raised to the power x. Then we have to find derivative of x, and we know that derivative of x with respect to x is 1. So we have to use 3 standard form for differentiate this composite function. So derivative of y we write dy by dx. Derivative of cosec inverse is minus 1 upon, in place of x we have value e raised to the power minus x. So we write e raised to the power minus x in bracket e raised to the power minus x its bracket square minus 1. So we use this minus 1 upon, in place of x we write e raised to the power minus x. Here also in place of x we write e raised to the power minus x into d by dx of e raised to the power minus x. This is first derivative. Now we going to find derivative of this second. So we write here minus 1 upon e raised to the power minus x. So we write this as e raised to the power. We can interchange the power. So or you can write this as it is, e raised to the power minus x its bracket square minus 1 into, now derivative of e raised to the power x is e raised to the power x. So we write derivative of e raised to the power minus x is e raised to the power minus x into derivative of this minus x. That means here we find a second derivative, first derivative, second derivative. Now we find derivative of this third term, that is derivative of third function, that is algebraic function. So we write here minus 1 upon e raised to the power minus x in root e raised to the power minus x its square minus 1 into e raised to the power minus x. Now derivative of x, this minus sign means constant. So we take this minus sign before this bracket, and a derivative of x with respect to x is 1. So this in multiplication form. So we write here square bracket. So we write this minus 1 into e raised to the power minus x as minus e raised to the power x, and this minus sign. So we write minus minus plus. So we write here, and in next step this e raised to the power minus x get cancelled with this e raised to the power x. So we write here 1 upon. Before that we write this as e raised to the power minus 2x minus 1. We write this e raised to the power minus x is bracket square. So we use the concept a raised to the power m bracket raised to the power n is equal to a raised to the power m into n. means we multiply the power, so we get here e raised to the power minus 2x, or you can write this e raised to the power minus 2x as 1 upon e raised to the power plus 2x minus 1. So you can transfer this e raised to the power 2x minus 1. So you can simplify yourself. Next step. So you can find a derivative in this way for this given function. So I solve one more step, but you try yourself. So 1 upon e raised to the power 2x, when we cross multiply, we get 1 minus e raised to the power 2x upon e raised to the power 2x. So we separate the root. So we write here 1 upon 1 minus e raised to the power 2x upon root of e raised to the power x its square. So we write e raised to the power 2x as e raised to the power x its square. So square and square root gets cancelled, and this e raised to the power x in denominator. So we write this in numerator. So we get e raised to the power x upon in root 1 minus e raised to the power 2x as a final derivative. Now see third sub question, cot inverse of x cube. So we write in solution, let y is equals to cot inverse of x cube. So we know the derivative of cot inverse x. Derivative of cot inverse x is minus 1 upon 1 plus x square. So here in place of x, value is x cube, that means this is composite function. So we have to find two derivatives, derivative of cot inverse and derivative of x cube. So we write here, differentiate with respect to x. Therefore derivative of y with respect to x is dy by dx. Derivative of cot inverse is minus 1 upon 1 plus x cube its square into derivative of x cube. First we find derivative of outer function, then we find derivative of inner function. So we write here minus 1 upon 1 plus, so x cube its square. So we write power in multiplication. So we write here x raised to the power 6 into derivative of x cube is 3x square. So this write in one step, minus 3x square upon 1 plus x raised to the power 6. Now see sub question 4, cot inverse of 4 raised to the power x. Now this question is similar to previous question because, sub question 4. In previous example, we write one formula, cot inverse of x is equals to minus 1 upon 1 plus x square, and instead of 4 raised to the power x, there is value x cube, that is x raised to the power n formula we use. Here we have to use d by dx of a raised to the power x. Derivative of a raised to the power x is a raised to the power x into log a. Here in our example, value instead of a is 4. So we find derivative of this given function. So for that we write y equals to cot inverse of 4 raised to the power x. So we differentiate this. So we write derivative of y as a dy by dx. Derivative of cot inverse is minus 1 upon 1 plus 4 raised to the power x its square into derivative of 4 raised to the power x. So we write this as minus 1 upon 1 plus. So we write power in multiplication. So we write 4 raised to the power x into 2 or x raised 4 raised to the power 2 into x into derivative of 4 raised to the power x is 4 raised to the power x into log 4. So we write this as 4 raised to the power x into log 4 upon, we write this minus sign first, 1 upon 4 raised to the power 2x. Now see fifth sub question. Here we have to find derivative of tan inverse root x. So first we write y is equals to tan inverse of root x. Now here we use two functions, tan inverse and root x. So we know the formula for tan inverse x and root x. Derivative of tan inverse x is 1 upon 1 plus x square. Derivative of root x is 1 upon 2 root x. So first we find a derivative of tan inverse, that is derivative of outer function, that is 1 upon 1 plus root x its square into derivative of root x. So square and square root get cancel here. So we write 1 upon 1 plus x into derivative of root x is 1 upon 2 root x. So we write this 1 upon 2 root x first into 1 plus x. So this is derivative of y equals to tan inverse of root x. So in this way you can solve remaining questions. So for that, first you have to write the standard form and first find how many derivative we have to find. That means how many functions include in that given function.